Thank you, Paul. I would like to take this opportunity to say that it's a wonderful experience at Carl School Mice, especially for central wave phenomena. It's been too short for me to gain all this awesome experience. But so why we image the asteroid? So this is a question that lots of people in this room is asking right now. So we as central wave phenomena was contacted from Southwest Research Institute to look into how to image the interior of such an object, asteroid. The motivation behind the study, as Paul always just said, is to gain an understanding about inside an asteroid structure, also as a physical property inside an asteroid, such as velocity, porosity, as well as the density model inside an asteroid. Compared to other objects in space, asteroids are relatively easy to study due to its very low acquisition cost compared to the other objects in space. There are other reasons why we want to understand inside an asteroid. Asteroids are remnants when planet being formed. Understanding about an asteroid would help us understand our own planet, as well as our own solar system. Recently, there's been a concern about an asteroid would collide on Earth. Understanding about an asteroid would help us predict the future devastation from such a collision. In long term, asteroids are the most accessible resources in space. We can use these resources for the construction material, as well as propellant for the future mission for the NASA missions. As I speak, European Space Agency is operating a mission called Rosetta mission. This particular mission is reached to the comet CK this month, May 2014, and we operate the CONSERT experiment or the electromagnetic experiment in August 2014. This particular experiment will orbit the source satellite around the comet itself, propagate the electromagnetic wave, radio wave, into the comet itself, interact into the nucleus of the comet, and receive the reflected and transmitted data at the receiver, which is placed on the comet. My project is to investigate the feasibility to understand and how to use this particular existed experiment to do our 3D imaging of interior of an object. Let's explore another question of what do we already know, what inside an asteroid. Scientists hypothesize that asteroid looks like a pile of rubble. Inside an asteroid would compose of two components, which have been shown in two different color schemes. The first one has shown in the darkest color, which is called rock. The rock have the lower velocity. The regolith, on the other hand, have the higher velocity and the softer material like a matrix that hold rock together. This particular model is come from the EROS 433, where NASA has been visited by twice. We get a very good idea of what the contour of an asteroid, but not inside. The distribution of the rock inside is spherical, and we use this to do our imaging project to get the structure imaging of this particular project. Now, I used the forward modeling of time domain electromagnetics finite difference to do this particular project. This wave equation is derived from the Maxwell equations under the assumption of free charges in the free space. I used the scalar assumption of this particular project. The scalar assumption will not retrieve the polarization as well of the radio wave. However, the kinematics of the wave will also retrieve from this particular equations, from the scalar equation. Therefore, we can use this to process our GPR data. This particular equation in the middle term is shown the diffusion terms. This diffusion term introduced when the wave propagates into the conductive medium, which asteroid is, and the wave will get attenuated. Now I use this wave equation to propagate the wave from the source location as shown in the black dot. In this particular experiment, it's 1.9 kilometer far from the asteroid target. The electromagnetic wave will propagate to the asteroid target and reflect it back from the asteroid target and receive only the reflected data to use in our migration process. Now, such a long distance, we will use such a long time, and it is very high computational cost for our modeling. What I propose to use is to shift our source function from the source locations using the analytic green function to the suspicious surface. The green function will use only the speed of light and shift the source function to the closer array in order to do our modeling in the low cost of computational. Now in each source locations, There we have different suspicious surface all around the asteroid target in 3D. The next panel. Oops, sorry. The next panel will show you the. I'm sorry. The next will show you the source data, which is which is received from the suspicious surface all around the asteroid target. And we can propagate this particular source data at this different suspicious surface and record our source wave field. If you look into our wave field that actually propagate inside an asteroid target in 3D, what we can observe from here is our wavefront is propagate inside an asteroid target, reflected, transmitted, and also attenuated because the introduce of the conductive medium. We receive the reflected data at the same suspicious surface. And this is the corresponding data that we get from the suspicious surface. Let's see the no attenuation assumption. As you can see, the reflected data go all the way to approximately 800 nanoseconds. But such an asteroid target is conductive medium. When we introduce the attenuation inside an asteroid, as you can see right now, where the attenuations take into effect. After approximately 5,000 nanoseconds, we can see the attenuation happen because the wave propagate inside an asteroid target if it toss back and forth. Now, we use so-called reverse time migrations in the shot record domain to propagate our wave and cross-correlate to get our RTM images. And this is the corresponding RTM images. On the left panel, is shown without attenuations, and on the right panel has shown with attenuation. Let's focus on different location in the green arrow. As you can see on the left panel, you can see some rock structure and sphere inside the XZ plane. However, we cannot see whatever on the right hand side or with attenuations, as well as the big rock structure as shown in these particular locations. What we can conclude from here is attenuation will take an important role in our imaging project. Let's explore another question of how many shots do we need to stack to be able to get a good image in order to do our interpretations. Now, I introduce you the geodesic sphere on the left panel. This particular geodesic sphere composed of different equilateral triangles that place on the sphere, which will digitize our sphere into the equal space. NS stands for the number of shots. The red patches represent the source locations. On the right panels represent the corresponding microwave shot record image for one shot. As you can see, we have the bad illumination for only one shot because we have the 3D images, and the signal to noise ratio is low. Now, if we increase the shot number into 10 using the geodesic sphere, we can actually distribute our shot all around the asteroid target and increase the illumination all around the asteroid target as well. With the 80 shot stack, we will get a better signal to noise ratio inside an asteroid target. In this particular case, I use attenuations to model and to image this. And when we get to the highest distributions of the geodesic dome, you can see on the right panel, this is the final migrate image for this particular discretizations. We can conclude from here that 80 shots can be a good candidate for our migrate image to be able to interpret our interpret our migrate image. Now, what is the good velocity model to use to migrate this particular data set and to get a good image? First, I use the correct velocity model with no attenuations, as you shown the migrate image on the right panel. If you focus on different green arrow inside an asteroid when I change to the different experiment with different velocity. When I introduce this smooth in slowness, as you can see, the locations is mislocated of the reflector inside an asteroid. When I introduce the average velocity model, which is most likely we will have as a starting model, the reflector also not as good as the correct velocity model that I used for the first experiment. Now this is open for the new project for velocity analysis, both in 2D and 3D for the future project. Let's see how can we acquire the multi-offset data to use in this particular case. Last year, I explained and also showing that we can actually do the multi-offset data in 2D. I showed the acquisition as well as the imaging theory in 2D. Now this year, I will introduce you to the 3D acquisition design. The asteroid target is normally moving along one axis of rotations. In this particular case, it's a z-axis with a very fast speed. We have two satellites, or we introduced the dual orbiter system, where we have two satellites moving around this asteroid target in a different speed. This particular moving different speed will create an offset between the reflected angle of different satellites. The experiment I compute right here have the transmitter, which is closer to the asteroid target at 1.9 kilometer, and receivers have the longer time period, which is 2.5 kilometers far from the asteroid target. An asteroid will move very fast in the spinning rate of 5 hours around the z-axis. Now, if you actually stand on an asteroid with a very fast speed on the asteroid reference frame, the data that we will get from the two satellites that are moving in the coplanar is this particular data. At the point of the pole, what we can do in the short record domain for our migrations, we just pick the source location and look at the receiver coverage, and then we can migrate that using this particular short record migrations. This is the representation of the receiver coverage. On the left panel, as you can see, the black dot represents the source location. The pink dot represent the receiver locations. At the pole, as you can see, it's limited to the only apertures of the receiver. On the right panel has shown the 2D representation of the source and receiver. The color scheme in the background is the unfold map of the asteroid surface, or the color also represent the distance far away from the centroid of an asteroid. As you can see on the right lower panel, we can have only a very limited acquisition, limited receiver, and this is bad for our imaging because we will have a very bad illumination for the receiver when we do our imaging project. Now, if we actually pick the point at the pole, which is always the case that it will have the most data and most repetitive because it's always come back to the same locations. And this is the corresponding receiver coverage that we will get. Still, we have more data and more coverage, but still it's only in the region because of the limitations. Now, this is not a deal breaker because such a small objects, we can actually shift the orbital plane of the object and actually get a better illumination or the better receiver coverage from different design. I propose here 6 different designs. Let's focus on the top left. The first design is when we shift our receiver plane in the longitudinal directions and still have the source location at the same place. The second design is when we shift it's in the inclinational direction. The third design is when we shift both source and receiver in the longitudinal direction. The fourth is when we shift both in the inclinational direction. And the fifth and the sixth design is when we have the combination of the inclinational and longitudinal direction of the plane shift. Now, I assume that every 500 hours, this orbital plane will shift. When we shift the orbital plane, we will create a coverage of the receiver all around the asteroid target. And this will give us a better illuminations as well as the better receiver coverage used in our short record domain. Let's see design 1. As you can see now, our receiver at the pole is not evenly distributed, but distributed all around the asteroid target. As you can see from both 3D and 2D representation. Let's see in 2D design 2 receiver coverage. The receiver will change the location as we go all the way to design 5 and 6. Each different design will offer us equally number of receiver placed on the asteroid target. However, it's not evenly distributed. So which design that we want to use? What I introduced is to use minimization level functions to discretize this. So this particular equations is just calculate how many receiver that fall into a particular area, subtracted from the average. This particular equation also scaled down from 0, where we have evenly distributed of receiver all around the sphere, and scale to 1, when all the receiver is falling to the only one patch. And this is the worst case scenario. What we introduce is we use the geodesic dome, again, to discretize our receiver in each design and calculate how many receivers fall into each patches and use that equations to discretize and also find the minimization level. This is the minimization level of all the design 1 to 6. As you can see, it's low enough to say that we have to distribute it all around the asteroid target. However, this particular design, all the design have eventually the same of the minimization level. What we can pick from here is the lowest cost of acquisition, where we only shift our satellite into the longitudinal direction. This is the corresponding design 1 with the migrate image as a very sparse receiver coverage. This is 10 chart stack. And now I have a question that, what about if I changing the receiver coverage into different design, how our migrate image will change? At the exact same chart location, this is design 2 with different distribution of receivers. Design 3, 4, 5, and 6. Again, all the designs from 2 to 5 to 6, I use only one chart record migrations to show. Right now, we can actually conclude that different receiver coverage will give us different migrate image, totally different migrate image, with the exact same velocity model we use. This particular case, we can actually conclude that with higher number of shots that we can stack, we can actually get a better insight of the asteroid target. But due to the time limited, I haven't shown in here. I would like to conclude that my project enable 3D imaging of asteroid targets and make it possible. The accurate velocity model is needed to be able to get the good migrate image. Multi-offset acquisitions is needed and attainable using the dual orbiter system where we have two satellites moving in different speeds. The dense coverage of data is needed, but it depends on the acquisition time, and acquisition time is directly depends on the acquisition cost. I would like to close my presentation by acknowledging the funding from NASA, as well as the great collaboration from Southwest Research Institute, especially Dr. Bob Grimm and Dr. Ruth Stillman. Thank you for your attention.